We want to confirm that the integral test can be applied to the following series. Then we want to use the integral test to determine convergence or divergence of the series. Let's first start off with the sum from n equals 1 to infinity of e to the negative n. So the conditions for the integral test are f has to be continuous, has to be positive, so the sequence a sub n has to be positive, and it has to be decreasing. So we're going to define f of n as e to the negative n. We know that this is an exponential decay. So clearly f is continuous. It's positive because it's always going to be greater than 0. It never reaches 0. That's a asymptote. So yeah, this checks all the three conditions. So now we can apply this. We can apply the integral test. So it'll just be the same bounds. So we have from n equals 1 to infinity e to the negative n dn. The antiderivative of e to the negative n is negative e to the negative n. Now we have to go from 1 to infinity. So technically we need to have a limit as b goes to infinity because this is a improper integral. Okay, so we can simplify this further. We're going to plug in b first. So that'd be negative e to the negative b minus negative e to the negative 1, which is the same thing as adding e to the negative 1. We know that this is an exponential decay, therefore this is going to go to 0. So what we're left with is e to the negative 1 as the integral answer. This is less than infinity, therefore the sum converges. Let's look at another one. We have 1/2 plus 1/5 plus 1/10 plus 1/17 plus 1/26. So this one, it would help if we can define, or we can come up with a formula for this. So let's say we start at n equals 1. So what might help you here is to identify the difference. So this is 3, 5, 7, and 9. And then if you look at the difference of the difference, it's the same thing. Okay. So whenever you have when you have to go too deep like this to find out the difference, that means it has to be a square or a quadratic. So it may help to write it like this. For the first term you get 1/2, which I'm just going to only look at the denominator. So this will just be 2. When n is 2, the denominator is 5. N is 3, the denominator is 10. Etc. So I'm going to look at n squared to help us out here. N squared, so that's 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So clearly we're 1 off. Okay, so we have to add plus 1 to make this equal. Okay, so remember this is just the denominator. So we can write it as 1 over n squared plus 1. Okay, now we want to go through the three conditions of the integral test. So the first one being it has to be continuous, and then positive, then decreasing. So we're going to define f of n as 1 over n squared plus 1. So let's see. we know that this is going to go to 0 in both directions, and when n is 0, this is 1. So it's going to look something like a bell-shaped curve, something like this. But for us, we're only interested, from n equals 1 to infinity. So obviously it's going to be decreasing, from n equals 1 to infinity. It's going to be continuous and it's positive. It's never negative because n squared plus 1 is always positive. Okay, so 1 over a positive number is just positive. So the conditions are met for the integral test. And now it's just a matter of applying the integral. We're going to use the same bounds as the sum. And this is nice because the antiderivative 1 over n squared plus 1 is inverse tangent of n from 1 to infinity. So technically here again we have to use a limit because it's an improper integral. But just so you recall, inverse tangent looks something like this. This is pi over 2. And this is negative pi over 2. So as it approaches positive infinity, it gets closer and closer to pi over 2. And then we just subtract this by plugging in 1. So the inverse here would just be pi over 4. So inverse tangent of 1 is really when tangent is equal to 1, and that's pi over 4. Okay. So it's really pi over 2 minus pi over 4, which is pi over 4 is our answer. And since the integral is finite, the sum is going to converge. Now let's look at another example. Okay, this one, we have 1 over the square root of 1 times the square root of 1 plus 1. So the plus 1 is outside of the parenthesis, or the square root. So we have 1 over square root of 2 times square root of 2 plus 1, square root of 3 times the square root of 3 plus 1, etc. And this is the nth term we're given is this. Okay. So that goes on forever. So for the three conditions, before the three conditions, because they give us the nth term, we can just write that as the sum here inside. And it starts at n equals 1 to infinity. Okay, so n here is 1. Okay, so let's look at the three conditions of the integral test. So first, it has to be continuous, has to be positive, and has to be decreasing. So let's look at these three. The easiest one to see is the last one. So as you move along here, the denominator is getting bigger and bigger, right? Square root of 1 is less than square root of 2, less than square root of 3, etc. So as the denominator gets bigger, your whole fraction gets smaller. So this is definitely decreasing. This is all positive because you're taking the square root of a positive number. Like you're taking the square root of a positive number, you're adding a positive number, dividing a positive number. So there's nothing, we're not dealing with any negatives or subtractions, so we're good there. Now for it being continuous, because we're interested in n greater than or equal to 1, the only time where it's not continuous is when the denominator is 0, which means the square root of n is 0 or square root of n plus 1 is 0. That means n is 0 here. Square root of n equals negative 1. Well, that's never 0. And the other condition is that you want, whenever you're taking the square root of something, you want it to be greater than or equal to 0. Okay. So n here cannot be negative, but because we have the restriction, We're looking for n greater than or equal to 1. We don't have to worry about this one. So to summarize this, for n greater than or equal to 1, the only issue is when n is 0, because it will be divided by 0, which is not part of our domain, so therefore it is continuous. So all three conditions are met. So now we can evaluate the integral. The bounds are going to remain the same. So that leaves us to integrate this. This is a little tricky, so what I'm going to do is let u equal the square root of n plus 1. So du is 1 over root n dn. So I'm going to ignore the limits for now. Okay, so this entire inside we said is u. So we're going to replace that with u. I have dn over root n. Dn over root n. Well, that means I have to multiply this 2 over to the other side. So that means 2 du equals dn over root n. And so that takes care of the root n on the bottom here. So it's really 2 over u du, and that's 2 ln u. So now we can switch back to n. So it'll be root n plus 1. And that would just go from 1 to infinity. And notice natural log, if I approach n to infinity, the natural log is going to be infinity. So let me write it like this. This thing goes to infinity, and this is a finite number. Okay, so the limit is going to be infinite, and which means that the sum is going to diverge, right? In order for it to converge, this has to be finite, but we got to answer that it's infinite, therefore it diverges.